Alright guys, welcome back to Pi, and today's derivatives, day 1, part 2. Let's get started straight away. So recap. So in my last video, I talked about 4 core rules for differentiation rules, and today I'm not actually going to, I don't think I'll be introducing any new rules. I'm just going to be reviewing some additional things that you should know about derivatives. They're not so much rules, but more of, I guess, just more information about derivatives. So let's get started. All right. So higher derivatives. All right. So the derivative of a function can be taken multiple times. Think about it as the derivative of a derivative, useful for many applications later on. So let me explain more about that. So basically, higher derivatives is that we don't necessarily need to find we are not limited in only finding the derivative of a function once. We can actually take the derivative of a function multiple times. So it's kind of like taking the derivative of a derivative, or the derivative of a derivative of a derivative. It's kind of a tongue twister. We can take the derivative of a function as much as we want, until, of course, the function probably either comes down to 1 or 0. Not quite sure. It was in my earlier classes. But basically, the point I'm trying to get across is that we can take the derivative of something multiple times. All right, so notation. So how do we represent, for example, taking the derivative of something multiple times? Let's say I have a function. So let's say I have, let me change it to the color blue here. Let's say I have a function f of x is equal to 3x squared plus 2. All right. So let's say I don't want to find the derivative. I want to find the second derivative. So how can I write that in using my all the types of notations that I learned for derivatives? So let's start with the Lagrange notation, which if you remember, for finding the first derivative, was f prime, which is the thing that kind of looked like an apostrophe, or y prime, same thing. And then the Leibniz notation, which was dy over dx, right? All right, so let's talk about how excuse me. So let's talk about how we can find the second derivative. So I don't want to just find the derivative. I want to find the second derivative, and I just want to know how to represent that. So how to write that in notation. So how to mathematically express that. So for the Lagrange notation, what you can do is, depending on the derivative you want to find, you simply add the same amount of primes, which is this symbol. So if you want to find the second derivative, the way you can express that is by writing this f prime prime of x, because double needs 2. So you want to find the derivative of the derivative. So the way you express that is f prime prime of x. Or for this method, you can just write y prime prime, and it's the same thing. Now, for this one down here, it's a bit different. The way you write it is so for example, if I'm finding the second derivative, the way I can write this is d2y all over dx2, right? It's a bit weird, but this is the other way of writing it. All right, so you have two ways of writing it. Depends on which type of notation you want to use. If you're using the Lagrange notation, you're going to be writing f double prime x or y double prime. For the Leibniz, you have to write d2y all over dx2. And this 2 does not mean you're taking the exponent. It just means you're finding the second derivative, because dy over dx is like finding the first derivative, right? And if you watched my earlier video, if you paid attention, you said that I preferred the Leibniz notation over the Lagrange notation, and I'll explain why. I just want to see, did I leave? Yes. Okay, I gave myself an extra page. All right, so I'm going to explain why I prefer this over this, right? I like the Leibniz more than the Lagrange, and this is the reason why. What if a question asked you, for example, find the ninth derivative? Find ninth derivative, right? if you were to use the Lagrange notation, you'd literally have to do this. F prime 1, 2, 3, 4, 5, 6, 7, 8, 9, x. All right. I know these kind of look like ones, but I mean prime. And if you want to use the other method of the Lagrange notation, you'd have to 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So this is clearly not practical, not practical, and it takes up a ton of room and very valuable room sometimes to answer a question. This takes up way too much room, and it's just not practical, and you can easily miscount or have the wrong number of primes, and it doesn't look very nice either. You have this thing going on here, which is very long. However, if you use the Leibniz, all you need to do is you want to find the ninth one, so all you do is d9y all over dx9. This means the ninth derivative. You literally just change the number of the derivative you want to find. This is why I prefer Leibniz, and I use it frequently. I mean, if I want to just find the first derivative or second derivative, sure, I will use the Lagrange method because it's just so much easier. It's very quick. You just draw a prime and you're done. But this can get not very practical if you have a lot of derivatives. And another note is that for high school calculus, they're not going to usually ask you for the ninth derivative because that can take a really long time to figure out, because you just have to be doing it over and over and over again, like 9 times until you find the derivative. They're usually going to be asking for the first or second derivative, maybe the third or fourth. But I just wanted to let you guys know because we can take higher derivatives. So it could be possible, but it's probably not very likely. But I just wanted to let you guys know. So basically I guess if you're still a high school student taking calculus, I guess the Lagrange can still be seen as an easier and better method. But if you're asked to find larger amounts of derivatives, then definitely Leibniz will be much easier to represent. Right, let's move on. All right, so your turn. So for example, for this for the function f of x is equal to x to the power of 9, find a, the third derivative, and b, the sixth derivative. All right, so if you want, pause the video and show your work, and then I'll be going over the answer. All right. All right, so let's go over the answers. So the function f of x is equal to x to the power of 9. So for finding the third derivative, it's actually the way you find higher derivatives is very simple. It just takes a long amount of time, at least at this level, at this stage, right? So all you have to do is you have to just repeat it. You have to repeat the derivative process 3 times to find the third derivative. So, for example, if I use the Lagrange method, since this is 3, it's still not too big of a number. So f prime of x, and if you guys remember from my last video, this is a power function. So the exponent comes down, and then we subtract from the exponent 1. So 9 minus 1 is 8, right? So the first derivative, hence represented by the 1 prime symbol, it's f prime of x is equal to 9x to the power of 8. Now, to find the second derivative, again, it's very simple. This time we have a constant multiple formed by the 9. So we ignore the 9 stays there, and then we just focus on this portion right here. We want to find the derivative of that. The 8 comes down, and we subtract 1 from the 8 for the top, which is 7, right? So, and to clean it up, it is 9 times 8 is 72, 72x 7, right? So that is the second derivative. Now we want to find the third, so still one more. We have to put 3 primes, which represents the third derivative, right? And 72, the 7 comes down. So we ignore the 72 because it's a constant multiple, times 7. And for x over here, we remember that we have to subtract 1 from the 7. So all we do is just 7 minus 1 obviously is 6. So we're just going to write the x to the power of 6, which we can simplify further, and 72 times 7, you may need a calculator, is 504, right? So 504x to the power of 6. And that is the answer for the third derivative of x to the power of 9. For part B, you're just going to be using the exact same method. And since you've already figured out the third derivative, you don't need to restart. Obviously, you can just work with this and work your way through. So I'm just going to be doing it really quickly here using my calculator. So for the fourth derivative, I'm just going to write fourth derivative is going to be 3024. It gets very large very quick. Fifth, this is going to be even bigger. The constant multiple is getting bigger. 15,120 x to the 4, and 6, which is the one I'm looking for, is going to be 60,480 and x to the power of 3, right? So that's your final answer for B. So one thing you can realize is that every time we take the derivative of a function, the constant multiple gets bigger, but then its actual exponent starts getting smaller and smaller until eventually the variable does not exist anymore, because you'll reach a point when you'll have 1, and then obviously 1 minus 1 is 0, and x to the power of 0 is just 1, so it multiplies by whatever constant you already have, right? So that's that. So now let's look at a new topic. So that was higher derivatives. Let's now focus on something called differentiability. It's kind of a long word to spell and to write as well, but it's a very basic idea. It's just whether a function has a derivative at a particular number. That says number. It's wrong. Should be number. Just going to delete that very quickly. Number. At a particular number. So differentiable, I'm looking at down here. Differentiable, the slope of the derivative is a defined value. Function f is differentiable at x equals c, and c in this case is just representing a function value, is equal to f prime of c is a finite number. So basically differentiability is just dealing with whether something actually has a derivative value. So if something actually has a slope of a tangent line, or an instantaneous rate of change at a specific point at a particular number. So that's all, because not everything is actually differentiable, not everything has a derivative. So that is one thing we need to keep in mind. So this is what differentiability deals with. It's just seeing whether something is differentiable or not. All right. So now I'm going to be talking about, there's a couple key cases which are definitely non-differentiable and you can't differentiate them, and that's what I'm going to be talking about. All right, so let's get into the first case, which is corners. You cannot differentiate corners, and this graph is very common with absolute values. So absolute values, if you remember, they're, for example, like this. This is the most basic. This is actually what this one represents. When absolute values, we have a point usually. In this case, it's at 0, 0. There's a corner right there. This is a corner. All right. And the reason why this is not differentiable is that because, remember, differentiability deals with the slopes of tangent lines. Tangent lines can only touch a point at, can only intersect a graph only once locally. And the point that they intersect at is called the point of tangency, or POT. Point of tangency, right? So we can only have, the key thing to remember, we can only have one tangent line for a particular point. So we can only have one possible tangent line. We can only have one possible tangent line, all right? And we cannot have more than this, right? So the problem with corners is that we can actually draw multiple tangent lines, and that is not allowed. For example, I can do this, I can do this, I can do this. So there's multiple options. There can be multiple tangent lines for that corner, and since we can have multiple tangent lines, this is not differentiable. There is no derivative for this. So there is no way to at that specific point to find the derivative for x is equal to 0. So remember, it's only at that point. The rest of these points, like here, 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 I can definitely find there's definitely a tangent line, and there's definitely a slope of a tangent line as well, because there's only one possible tangent line that can touch that particular point, such as here, here, and here. However, for this point, since it's a corner, there can be multiple tangent lines. Therefore, there is no tangent line because we can only have one possible tangent line. Since there's multiple, that means there's no tangent line, and that means there's no slope of a tangent line. That further means, therefore, it's not differentiable. Now let's move on to the second case, a cusp. So a cusp is just basically just two arcs. It's the point created due to two arcs, right? So the cusp in this example, I'm going to be using the blue color. The cusp is right here, right? We can clearly see it. Again, it's similar to a corner. It's a sharp point, and it's the exact same problem. I'm going to select this color. I can draw multiple tangent lines here, right? So I can draw multiple tangent lines. Since there's multiple tangent lines, it's not differentiable because we can only have one possible tangent line. Therefore, a cusp is also not differentiable. All right, let's move on. Vertical tangent lines. All right. So with this one, I think this is a graph of f of x is equal to x cubed, right? So with this one, the problem is it's not so much that we have multiple tangent lines. For x is equal to 0, we have a vertical. Oops, that's not. We have a vertical tangent line. So we have a tangent line that goes like this. This is, I know it's not perfect, but this is supposed to intersect x at 0. X at 0. This is supposed to be the tangent line for that. Now, what the problem here is, it's not that the fact that you can't draw multiple tangent lines, is that the tangent line itself is undefined. So if we go back to slopes and I guess the x-axis, y-axis, and rise over run and all that good stuff, we can remember that when we have a line that goes like this, that's straightforward on a graph. Let me draw my graph. This line, sorry, that's just a bad example. Just going to fix that really quickly. If I have a graph and I have a vertical slope, the slope is undefined. And the reason for this is that because this x value here has multiple y values, and we cannot have that because that means it is no longer a function, all right? So this essentially means that at that particular point, for x is equal to 0, the tangent line is undefined. Since we have an undefined tangent line, we do not have a slope of a tangent line, therefore we do not have a derivative, so it is non-differentiable, and that's why for vertical tangent lines, that is also a problem. Again, please note, it's only for when x is equal to 0. For all these points here, like here, 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 I have tangent lines because I can draw there's only one possible solution, and they're not vertical tangent lines. If I have a tangent line that goes straight through, that is allowed, because if I have a tangent line that goes like this, I have the same y value for different x values, which is allowed. That is classified as a function, but I cannot have two or more y values for the same x value, and that's what I have going on here, and that is not allowed, right? So that's why vertical tangent lines are basically mean that it's non-differentiable. So in this case, at again only x equal to 0, this is non-differentiable. All right, moving on, discontinuities. Again, this might go back to grade 12 pre-calculus or grade 11 pre-calculus with graphing. You might remember that we have things called discontinuities. So sometimes on a graph at a particular point, at a particular x value, again here it's for x is equal to 0, we might have a discontinuity, meaning that the graph is not necessarily connected at that point, and there's one value of the graph for that particular point. Another one is a discontinuity. So this one's a discontinuity. It's represented by a hollow circle. And so the problem with this, for why anything that has a discontinuity, the reason why it's not differentiable is similar to what we just talked to. just going to draw it very quickly. I can draw multiple lines here for the tangent. And here I can actually draw no lines because it's discontinuous. So since there are these two problems present, again, I can draw multiple lines because it's pretty much a corner. It's a pointy edge in a sense. I do not have a tangent line because there's multiple possibilities. And since I have no tangent line, I have no slope of a tangent line. And since I have no slope of a tangent line, that means I have no derivative. So this is not differentiable, sorry. So to summarize, the general condition is that a function is not differentiable where there is a corner, cusp, discontinuity, or vertical tangent line. Other than those four main conditions, a function will be differentiable. And it's very helpful if you can get a graph of that function and of its derivative so you can see if those conditions are present. Because a lot of times if you're not given a graph, you pretty much just have to know or memorize how that graph looks like. So for example, you might not have necessarily known that at x is equal to 0, you might have forgotten that x cubed, the graph of x cubed actually looks like this. So it's very helpful to actually graph it out first if you guys obviously have extra time, or to get to know this topic better. If it's really helpful to graph it out first and see if you have any of these four conditions present at a particular point, because if you do, that means at that particular point that function is not differentiable. And that's it for today's video. Thank you so much for tuning in. Please check out my website in the description. Again, like I said earlier, I have extra notes in full detail. I have practice problems with varying levels of difficulty, and I have solutions to those problems with full work shown so you guys know how I got my answer. And again, thank you so much for watching, and stay tuned as I continue to talk about this derivatives unit. And thank you so much. Have a great day.